Hey everybody, I just want to give you guys a little bit of an overview of chapter 1, and please still read chapter 1. It's got more information, but I'll give you a brief summary. This will also give you an opportunity to take a look at the skies system. And actually, as this video is playing, I want you to open up skies, take a look at it. Now to get to skies, we've got Moodle. Our course code is here, although it's built into the link. So you can just click on that and it'll bring you to our course. And feel free to pause this video if you need to sign up for Skies or if you need to register with the course. Take your time. I'm not going anywhere. All right, so chapter 1 opens up with this parable of surveyors. You've got one surveyor using magnetic north as the barometer, so to speak, or for orientation. And they've got two measurements or two systems of measurement. We've got north-south, and they're using miles for that. And east-west, they're measuring in feet. You got a second group. This is a different observer, right? We've got observer 1, now we've got observer 2. They're using the North Star as their north. Still using the same north, south, east, west with the miles versus feet issue. Anyway, the takeaway from this is that they're both measuring the same thing. They both got a different observation, so things are a little bit skewed perhaps, but they're measuring the same thing. The distances work out the same. They can use one system of measurement overall. They don't need to use miles and feet. They could use one or the other. So too with space and time. Yes, we can equate space and time more or less. The difference is that you can't move backwards in time, and the equation for the distance is a little bit different. Here we call it the invariant interval. And a really cool thing about special relativity is that you don't need to know any of the background really to be able to calculate changes in length or time if you're able to manipulate this interval. So the interval squared, that's the analogous case to our distance, is the time separation squared minus the space separation squared. And note that you have to have the same units of space and time. And that interval is going to be the same regardless of whether you have observation group 1 or observation group 2. It'll have the same interval. And so it works both ways. Say we've got a rocket that's moving, blasting off. Space time, rocket time squared minus rocket distance is equal to lab time squared minus lab distance. Boom. You don't need to know anything else about time dilation or length contraction or anything like that. And you can still calculate what it is just because you have this equation in your back pocket. So now wait, what's this whole time is length thing that I was saying? Okay, well, you want to have consistent units for space and time, kind of like that whole parable of the surveyors, right? And to do this, you just simply divide or multiply by the speed of light. So if you want time units, you take length and you divide that by c. If you have a length, if you have time and you want length units, multiply it by c, right? Because that's just going to be time times the velocity. Velocity is distance over time. Therefore, you get a distance. And here's a quick example. So how many meters of time are in one day? Go on, work it out, and select one of the responses there. Be interested to see what you have. Go on, pause the video. All right, and the correct answer is the first choice, 2.59 times 10 to the 13th. You just take one day, which has 24 hours, with each hour having 3,600 seconds. So you multiply the number of seconds by c, and you get that as the result. Okay, now let's do it the other way. How many seconds of distance are in 1,600 meters, which is 1 mile? Pause the video. All right, so this time we just divide the distance given by the speed of light, and we get a very small number. That's how many seconds of distance are in 1 mile. Okay, now let's try an example where we are using the invariant interval, both sides of it, in order to figure out the difference in either length or time. So in this case, we've got two firecrackers explode at the same place in the laboratory. They're separated by a time of 3 years. What is the spatial distance between these two events in a rocket in which the events are separated in time by 5 years as measured by the rocket clocks? And now here, this isn't a multiple choice question. Instead, you can just type in whatever your answer is. I'll give you a minute to do that. So here, going back to our invariant interval equation, what are we given? Well, we're given the rocket time, right, 5 years. We're given the lab time, 3 years, and we're given the lab distance, which is 0. And then what is the rocket distance? Well, the distance according to the rocket. Just plug those in and solve. And here you have it written out. We've got 5 years, 3 years, squared, squared. That means that our rocket distance is going to be 4 years. And that's 4 years in our distance time metric, right? Well, that's all for now. If you have any questions, email me. You've got my info, and I'll see you in class. Thank you.